Welcome to this NPTEL lecture on principles and techniques of modern radar systems. So, in the last class we have started seeing the hardware components, those are necessary to have the monopulse ratio. So, in that we have seen feeds, then we have started seeing the hybrid junction. Now, hybrid junction we have discussed that it is a 4-port device. There are 2 input ports, there are 2 output ports, and 2 properties are required from this hybrid junction. One is that if we give the signal to port 1, it should not come to port 2, and power should get equally divided between the 3 and 4 output ports. They may be in phase, they may be in quadrature, but power should be equally divided. And also we have seen that if 2 signals with proper phase are applied to the input ports of the hybrid junction, 2 input ports of the hybrid junction, then in one output port we should get sum, in another we should get the difference. Output will be proportional to this. So, now the relative phase between the 2 inputs, that depends on the particular type of hybrid. It is either 0 degree or 90 degree. So, now we will see that some of the examples of this thing. So, that first that we will see is called a magic T. You know, we in undergraduate courses you have seen this. Also you can refer to the NPTEL lecture on basic components of microwave engineering. There we have discussed the principles of this in detail. Magic T, there is nothing magic in it, it is basically combination of one E plane junction and one H plane junction, and here this is a magic T. So, this 1 and 2 are the input ports, 3 and 4 are the output ports, and we know its S matrix, the scattering matrix, that is given by minus j by root 2. Please remember, scattering matrix is the voltage wave ratios reflected by incident. So, that turns out to be 0 0 1 1, then 0 0 minus 1 1, and 1 minus 1 0 0, and 1 1 0 0. So, this is the S matrix. So, from this S matrix we can say few things, that if when the input is given at port 1, we can see that equally that gets divided to port 3 and 4. You see the first column. So, that is if the input is given to port 1, then equally it gets divided between the ports 2 and 4, and nothing comes out of port 2 because of this 0. Similarly, when input is given to port 2, then also equally divided to port 3 and 4, nothing comes out at port 2, but you see that the in port 3 signal and port 4 signal is out of phase in case of if the signal is given to port 2. If the signal is given to port 1, the signal at port 3 and signal at port 4 are in phase. So, we can say that if simultaneously 2 signals are given at port 1 and port 2, so then their sum will be appearing at port 4 and their difference will be appearing at port 3. So, 1 and 2 inputs, if they are in phase, then S and D output also will be in phase, and input and signal and output signal differs by propagation phase, but that is immaterial because relatively that does not matter. So, theoretically this is the behavior, but actually it is a frequency sensitive behavior because this length of these T's. So, they are designed for a particular frequency. So, they are not broadband. So, if your signal has a bandwidth somewhat larger, then there will be problems, but that is a thing. So, let us first discuss the ideal things. So, let us say that V 1 is the input voltage at port 1. Remember, yesterday we have discussed in detail that this V 1 is actually a complex voltage, because this is an RF signal, and let V 2 is the input voltage at port 2. So, from the scattering matrix easily we can write what will be V 3. V 3 will be minus j by root 2, V 1 minus V 2, and V 4 will be minus j by root 2, V 1 plus V 2. Okay. So, depending on polarity convention of V 1 and V 2, V 3, V 4 may get interchange, but we should always have that one output port we have the signal is proportional to sum, and in one output port it is difference. Now, the factor of this root 2 is coming to make the power balance. So, we can check that if we find what is V 3 square plus V 4 square, that becomes V 1 square plus V 2 square. That means, power balance is there between the input and output. That is required because we are assuming a lossless T junction. So, and also the input and output are interchangeable. That means, we can make 3-4 input ports and 1-2 output ports. Okay. So, this is one example, this you are familiar with the magic T, but magic T has one problem, that construction wise this port 4, that means, the plane this port 2 that is in a different plane. So, it becomes a bit more bulky. So, in cases where we have planar type of thing, it may not be suitable. So, the second example we will see that another example of hybrid is rat race. So, this is also an example of a hybrid. Here the in a rat race, you know, it is a transmission line based structure. So, there are 4 ports, let me call this as 1 and this is 2, these are the input ports, and let me take some other color. So, this is 3 and this is 4. Now, construction wise this distance is generally taken 3 lambda g by 4, lambda g is the guided wavelength. So, and these are all lambda g by 4. So, if we give signal at port 1, you can see that it reaches, the signal reaches port 4 by two different paths. One is having length 3 lambda g by 4, another is this 3 lambda g by 4. So, path difference between the two signals that are travelling to port 4, they are 0. So, they gets reinforced in port 4. Similarly, the same signal reaches port 3 by two different paths. One path is 5 lambda g by 4, that means basically lambda g by 4, and another is this. So, again the path difference is lambda g. So, that gets reinforced. Then it reaches port 2 by two paths, the path difference between the two, that is lambda g by 2. So, they cancel out. So, nothing comes from this. So, they are satisfying the property, the first property of rat race, that if signal is given to 1, it gets equally divided between 3 and 4 output ports, and in port 2 it does not come. Similarly, if we give the signal at port 2, then you can check from this that equally they get divided into 3 and 4, and nothing comes out at port 1. And so, if same phase signals are given at port 1 and port 2, then you can see the sum will be at port 3 and difference at port 4. So, S and D are in phase. So, phase relationship of rat race, you can see explicitly the construction is done at 3 lambda depending on lambda g by 4. So, depends on lengths the phase relationship. So, it also is a narrowband device. So, this is another problem, because actually we will be dealing with pulse. So, we require a bit more broader things. So, we will see the third example of hybrid, that is a directional coupler. This also you all know from your study of microwave engineering. Also, you can see that these couplers we have discussed in detail in our NPTEL course on basic building blocks of microwave engineering. Now, what is a directional coupler? A directional coupler is actually so there are two holes, two openings here, and actually this is the primary guide and this is the secondary guide, and so we can say that the waves, they are coming here. So, they will come here, also one will go on, and again here there will be a path here and this wave will go, and similarly these waves they come here, they also go here, and this wave also comes here and goes here. And now, let us give the names. Let us say that port 1 is here and port 2 is here, the two ports, and let us say this is port 3, this is port 4. So, what is a coupler? Just I am refreshing your memory that a coupler is a device that taps off some fraction of the power flowing through a primary waveguide or transmission line into a secondary waveguide or transmission line. The coupling factor, you will know the coupling, this is the characteristic parameter of any directional coupler. So, this is primary input power by the power directed to secondary output, that means output in the secondary guide. So, if I give power here, whatever power I am giving, input power divided by the power in port 4, because this is the secondary guide. If I give power in the port 2, then this will be primary, this will be secondary. So, that time it will be power given here divided by power in port 3. So, this you know. Now, monopulse will require 3 dB couplers. So, 3 dB coupler means that the primary output power and secondary output power, they are, you can say, diverted. This is, to be more precise, it will be power diverted. Diverted to this. So, 3 dB coupler means the coupling factor is 2. So, primary output power, it shows that primary output power is equal to secondary output power. So, now a directional coupler. So, previously I have defined coupler. Now, what is a directional coupler? A directional coupler is one that produces an output at a given secondary port when power flows to the primary port in one direction, but not in the other direction. Again I am repeating, a directional coupler is one that produces an output at a given secondary port when power flows to the primary port in one direction, but not in the other direction. So, in monopulse you will be requiring a 4 port directional coupler. In labs I think you have used 3 port directional couplers. There are also 4 ports are there, but one of the port, generally the second port is isolated. So, only in one you give the power, but in monopulse operation the hybrid that we require, if directional coupler goes there, that will be the 4 port. So, so now if we give signal, say the, so let me write 4 port directional coupler. So, produce output at one primary port and at one or other of 2 secondary ports, depending on direction of power flow in primary path. Now, if I give signal, or let me use this one. So, signal at port 1. Suppose I have given the signal at port 1. So, what I will get? I will get output at port 3 how much power I will get? That input power minus power diverted to secondary. Also, I will get output at the secondary port, that is port 4, and since it is directional coupler, no output at port 2 because it is directional. Similarly, if I give if we give signal at port 3, then we will get output at port 1, output at port 2. You can easily check from the diagram because I do not know whether I have indicated the construction. Right. Signal at port 3. So, output at port 1, output at port 2, no output at port 4. I am not able to locate. So, here one details I have not given, that this is lambda g by 4, then only you will see that in this direction the signal path difference is such that they are getting cancelled. So, I can say if I give power here, it is cancelling here, and here they are getting added, in port 3 it is going. So, this thing I think you all know. So, now we will see the for the 3 dB coupler, we will write quantitatively this thing, that I said that we require a 3 dB directional coupler, 3 dB 4 port directional coupler, and you know when all the ports are match terminated, that means there is no reflected power from the ports, after going to the output it is getting extracted. So, in that scenario, let V 1 is applied at port 1, V 1 applied at port 1. So, we know if we give port 1, there will be output at port 3, there will be output at port 4, they will be equal because of 3 dB. So, 3 and 4 will get equal power, but what will be the phase relation, now we should see that. So, if we see that V 3, that will be V 1 by root 2, again 3 dB power. So, in voltage terms that will be V 1 by root 2, and what will be V 4? V 4 will be either plus or minus j V 1 by root 2. Now, why I am saying plus j? Because this is depending on the construction of the coupler, as we earlier discussed that in case of hybrids you can have a 0 degree or 90 degree or plus j or minus j type of couplers. So, depending on construction of coupler, this whether you will have plus j or minus j. Now, let us see this drawing. So, you see these holes, they are the coupling paths. Now, the holes, if they are in the broad wall or broad wall of a coupler, then that means holes are in broad wall, then we get a plus j. That means, if the in a rectangular waveguide, this is the rectangular waveguide. So, this is the broad wall. So, this or the bottom one. So, if the holes are there, that is a broad wall, holes are in broad wall, that time plus j will be the phase change, and if the walls are in the narrow walls, this blue color is the narrow wall, this side or the back side. So, if the holes are there, then also you can have the coupler. So, then you have the minus j phase gets added. So, I will write that which sign to take, that depends on the construction, depending on construction. So, depending on construction, plus j or minus j in V4 signal phase. Now, the side wall coupler. What is a side wall coupler? That holes are in narrow wall. I have already indicated which is narrow wall of an waveguide. Then we get minus j. On the other hand, if we have a top wall coupler, then holes are in broad wall, then we have plus j. So, this choice is open to the designer, based on compactness required, he can choose either of the drawing. So, now similar thing we can write for V2. So, if V1 and V2 are applied simultaneously, so V1 and V2 applied simultaneously, that means V1 is the voltage applied at port 1, V2 is the voltage applied at port 2. So, what will happen to port 3? So, V3 will be V1 plus minus j V2 by root 2, and V4 will be plus minus j V2 plus j V1, j V1 plus V2 by root 2. So, in both the equations, depending on the coupler, suppose you have a side wall coupler, then in V3 expression you take this minus sign, and in V4 expression you also should take minus sign here. If you have a top wall coupler, then in this expression you have plus sign here and here also plus sign. So, that should be that you cannot interchange that. So, the same sign of the quadrature term applies to both equations. So, now you see that V3, V4, if we want to make sum and difference, then V1 and V2 should have a phase difference between them. This is clear because this is not directly giving you the sum and A, because there is a phase here. So, there are various possibilities. So, to make V3 and V4 sum and difference type of thing, what we need? We need that V1 and V2 should have a relative phase between them, relative phase. We will see one or two choices. Suppose case A, that let we put a phase shifter of phase shift 90 degree. So, that means V2 signal that we put to a phase shifter of, so that will give, let us say, 90 degree phase, and we call that V2 dash. That we apply to the directional coupler. That means, V2 is delayed by 90 degree by a phase shifter preceding the input. So, what will be output to port 2 of coupler? So, that means, what is the relation between V2 dash and V2? I can say J V2. And let us say that we are making a top wall coupler. So, now we are freezing the design. So, top wall, let us say, that means plus sign only I will have to take. So, now I can write in this case what will be V3 dashed. You see, I am writing V3 dashed to differentiate it between this case, that where V1 and V2 are in phase. Here there is a phase difference, that V2 is delayed by a 90 degree. So, if you do V3 dashed, it will be V1 plus same as this plus J, instead of V2 I should write this divided by root 2. So, this is nothing but V1 plus, but what is V2 dash? J and J. So, that will give me a V1 minus V2 by root 2, and what will be V4 dashed. So, V4 dashed will be that plus J V1 plus V2 dashed by root 2. Now, put the value of V2 dashed. So, plus J V1 plus J V2 by root 2. So, it is J by root 2 V1 plus V2. You see, now, if I have this relative phase between V1 and V2 by 90 degree, then the third port is giving me difference and fourth port is giving me sum. Now, there can be other choices also. You can see that if I have case B, then let us say that the picture is V2, then we put a phase shifter, but here it is minus J, and let us call that V2 double dashed. So, in this case, if you do, you will see that V3 double dashed, that will be V1 plus V2 by root 2, and V4 double dashed will be J V1 minus V2 by root 2. So, whether you want to make the third port as a sum port or difference port, these are the two choices you can make. Also, if you instead of a top wall coupler, if you take a side wall coupler, the whole thing will change. So, but the important point is, one of the output ports is giving me a signal proportional to sum, another is giving me a signal proportional to difference of the two input signals. So, that what we are looking for earlier. So, in the directional coupler we can have that, and directional coupler does not have like magic T any as or any different horizon vertical planes. So, it is easier to construct. You can have planar structures of this also. So, this coupler, that means is called quadrature phase coupler, various names of this coupler. So, quadrature phase coupler, or it sometimes is called 90-degree coupler. So, all these are different names of the same coupler, sometime called quadrature hybrid, sometimes called 90-degree hybrid, etc. Now, spacing of the holes, that you have seen that since it is lambda g by 4. So, that lambda g is calculated for a particular frequency. So, it is narrow band. So, how to make it broadband? People have researched that and found out that if you use more number of holes, that means instead of 2 holes you have more holes, or if you instead of holes you can have slots cut, that frequency sensitivity is reduced and that makes it broadband, and so then the device can be used over a useful frequency range. You know that the radar pulse is a narrowband pulse, but at least over that pulse the thing should work. So, that people have achieved. So, we have seen these examples of hybrids. So, we have discussed magic T, we have discussed the rat race, and we have discussed the directional coupler or this 90-degree hybrid. So, we saw that they can give the sum and difference, but our ultimate thing is that monopulse ratio, that how to make, that we have not till got. So, in the next class we will discuss that how to make using these hybrids, phase shifters and other circuitry, how we can design a hardware circuit which can give us the monopulse ratio D by S, or that is a complex ratio, or D by S cos alpha sort of thing if D and S are real. So, that thing we will discuss in the next class. Thank you.